Inductor inrush current stress. Inductor consists of the winding and the steel core. Between the core and the winding there is the insulation layer. Inductor operates on alternating current. When inductor is energized, the inrush current could be several times higher than normal full load current. Our task is to calculate the inrush current peak value and to compute mechanical stress in the winding. Voltage source root mean square value is 18 volts. Winding number of turns is 600. AC frequency is 60 Hz. This problem is essentially multiphysics. First, we should simulate transient magnetic problem to compute current versus time dependency and magnetic forces. Then we should parse magnetic forces to stress analysis problem to calculate mechanical stresses. Let's run QuickField. I create new problem. Problem name Inductor. Next. Problem type is transient magnetics. The geometry of the inductor features cylindrical or axial symmetry, so the model class is axisymmetric. Length units are millimeters. I will also add the electric circuit to the analysis. Next. In transient problems we should specify integration time and time steps. Well, the AC frequency is 60 Hz, then the sine wave period is 16 milliseconds. Let's choose the time step to be 1 millisecond. And I would like to simulate at least 10 periods to make sure that the inrush current has passed and we have reached normal operation mode. So 0.16. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. I have the geometry model already prepared. Here is the file. Open. In QuickField, the axis of rotation is a horizontal one, so the geometry model should be placed above the axis, and we should remove all parts located beneath the axis. So you can see half of the inductor here. Well, we have the inductor geometry here, but the magnetic circuit is open, so the magnetic field should pass through the air. We should add the air to our model. Switch to the insert mode. And add the surrounding area. This space would be the air. To distinguish one geometric object from another, we should assign labels. Through labels we also assign physical properties. Switch to the select mode. Click to select the object. Then open the properties dialog and type in the label here. This would be the air. OK. Now this is steel. And this is the winding. and there should be insulation somewhere here. Let's zoom in. Switch off zooming mode. Click. This is the insulation. And this space between the turns is the insulation too. Hold the Ctrl button pressed to select multiple objects at the same time. Okay, I have selected all the blocks located between the turns. Open the Properties dialog and select the label Insulation. Okay. Now you can see all new labels in the tree with the question mark. We should specify physical properties for these labels. Double-click the label Air. For the air, I specify a relative magnetic permeability of 1. Okay. The same for the insulation. 1. Okay. For the steel, I specify a relative magnetic permeability 2000. Okay. And for the winding, we specify a relative magnetic permittivity of copper, which is 1, and electrical conductivity of copper, which is 56 megasiemens per meter. And remember, we have assigned the same label, winding, to all 600 turns. Now I will specify that these turns are connected in series. I have added electric circuit, so the voltage source I will specify in the electric circuit. Okay. That's all for materials. Next, let's deal with the boundary conditions. Far away from our inductor, magnetic field fades to 0. So I give label 0 to external boundary. Remember, hold the Ctrl button pressed to select multiple objects. Properties 0. Okay. And for this label I specify 0 magnetic potential. We have another boundary, the axis of the rotational, but QuickField sets default conditions automatically to the axis. There is no need to assign label to the axis rotation. That's all for geometry model and the labels. Next, proceed with the electric circuit. Double click, yes, create circuit now. We should put all conducting labels in the circuit. In our case, it is the winding. And we will add the voltage source. Then we connect the voltage source to the winding with the wire. The voltage source is a sinusoidal one, so we should type in equation here. 18 volts is a root mean square value. The magnitude is times square root of 2. Then goes the sine function, and here we have 2 multiplied by p multiplied by frequency multiplied by time. QuickField operates in degrees, not radians, so we should type in 180 degrees instead of p. Okay. The last step is to build the finite element mesh. Click the button. Now we can run the analysis. Yes, save all simulation files. The simulation process has completed in about 14 minutes and we can see the results now. Here you can see the magnetic field lines and the color map of the current density at the final moment of time. We can adjust the field picture. I can switch on the color map of the flux density. I can switch on vectors of the flux density. And we can get the field parameters in some points. I will use the local values tool. Then I can click any point and get the field parameters. And you can edit the point manually. We can also use contours to make plots or calculate integral values. If I select the wire, I can calculate the integral, total current or mechanical force, and I can see the time plot. Right click, time plot. This is the inrush current and it reaches the peak value at about 7 milliseconds. Let's take a look at the field distribution at this moment of time. In transient problems we can switch presentation time, 7 milliseconds. So this is the peak current value and this is the force acting on this conductor. And if I click another conductor and select the first one, I will get some other value of the force acting to the left. And there is some force acting on each turn and on the steel parts. And I would like to pass magnetic force distribution from magnetic problem to stress analysis problem. That is done through the problem linking. But first I should create stress analysis problem. Problem name inductor stress. Next. Problem type stress analysis. Model class the same axisymmetric. Length units millimeters. To be able to pass data from one problem to another, both problems should be based on the same geometry model. In our magnetic problem, the geometry model file is inductor.mod. So here I click in the geometry model, press browse and find the file. Here it is, inductor.mod. Open. Okay. You see the geometry model is the same and the labels are already assigned to the objects, but now we should specify mechanical properties. We do not calculate mechanical stress in the air. So for the air I do not specify any values. Just open and click OK. Now instead of the question mark we have the exclamation mark. This mark indicates that this is not an unknown label. This is the label with empty dataset, and this label is excluded from the simulation analysis intentionally. For the steel, the Young moduli is 200 gigapascals and Poisson's ratio is 0.3. Okay. For the winding, which is made of copper, Young's modulus is 100 gigapascals and Poisson's ratio is again 0.3. Okay. For the insulation, Young modulus is 5 gigapascals, and Poisson's ratio is 0.45. Okay. Zero boundary condition has no physical meaning in stress analysis problem. Again, I open the label properties dialog and do not specify any values, just click OK. We have finished with material properties. Now let's set up the link. Open the properties dialog and follow to the links tab. Here choose the imported data type, magnetic forces, and browse for the problem file, which should be inductor.pbm. Browse inductor.pbm. Open. Then add the link. Remember, in transient problem we have a sequence of time layers. We would like to import magnetic forces at the moment of their maximum. So I type in 0.007 milliseconds. Update. OK. Now the link has appeared in the tree and we can start the analysis. Yes, save all simulation files. We have the error message, not enough boundary conditions. What does it mean? There is a magnetic force acting on the winding and inductor, but there is no restrictions to the inductor displacement. Let's imagine that inductor is placed next to the wall and fix the inductor bottom side. Select the edge, open properties and type in the label fixed. And for this label I specify zero displacement in Z direction. R stands for radius, and in cylinder it points up, it's a vertical axis, and Z is a horizontal axis. Okay, now we can solve the problem. And again we get the error message. The linked problem results are out of date. What does this mean? We have modified the geometry model. We assigned new label to the edge. We have specified properties in stress analysis problem, but no properties are assigned in the magnetic problem. Well, this label has no physical meaning in magnetic problem, so I do not assign any data here. Just click OK, and you see the label is marked with 0. Anyway, the problem setup has changed, and we should run the simulation process again. So I will start the simulation of the magnetic problem. Yes. Now the magnetic problem is simulated again, and we can take a look at the results. Let's switch to the electric circuit results and take a look at the current versus time dependency. The current peak value remains the same. This label is marked 0 and doesn't affect the results. So we can proceed with the stress analysis now. Run the analysis. Yes, save simulation files. No more error messages this time. And here we get the result. You can see the deformed shape. In fact, it is scaled many times. If you switch on the color map of displacement, you will see that the maximum displacement value is between few micrometers. But let's check the stress distribution. The highest stress value is inside the steel parts, but the steel is tough. The insulation is much weaker than the steel, and the stress value in the insulation is of most importance here. Again, you can use the local values picker to get to know stresses in specific points. Or you can use the contour tool to make plots. I click this edge and switch on the XY plot. This is the stress distribution along the edge. You can see all the data used to make this plot in the table. Here you can choose which values to display, and you can specify the tabulating step. You can copy all the data, or you can save the table as a text file. You can find the page related to this example at our website. There you can read about problem setup and download the simulation files.